Okay, so we're in chapter 3, which is on organic molecules. We're now in section 3.3, which deals with lipids. Now, we've covered carbohydrates prior to this. Now, lipids are unique in that they are nonpolar and they are hydrophobic, meaning they are not water soluble. So they are somewhat similar to hydrocarbons. Remember, a hydrocarbon is a molecule that contains only carbon and hydrogen. Lipids are not true hydrocarbons, but they contain mostly carbon-hydrogen bonds with just a few oxygens in the lipids, and that's what makes them non-water soluble. It's mostly nonpolar covalent bonds. Okay, the most common lipid that we encounter is triacylglycerol or triglyceride. Typically when you go to the doctor and they check your blood, they'll report on blood triglycerides. Your textbook uses the term triacylglycerol. Basically, it means fats and oils. Okay, so this is the most common type of lipid. Now, the main function of triacylglycerols is that they serve as highly concentrated means of storing energy. As a matter of fact, the fats and oils, which again, triacylglycerol is just a fancy way of saying fats and oils. Fats and oils contain about 2.25 times as much energy as a carbohydrate on a gram for gram basis. And triacylglycerol, when we look at the structure of this, it consists of glycerol, which is an alcohol, and 3 fatty acids. Now, there are also monoacylglycerols and diacylglycerols, and as you would guess, monoacylglycerol has glycerol plus 1 fatty acid, diacylglycerol, glycerol plus 2 fatty acids. Okay, here's a diagram from your textbook showing this idea of a triacylglycerol, and it consists of the glycerol unit. Well, right up here is the glycerol unit, and you notice the OH on there. And then here's the fatty acid, and we have this carboxyl end, and the carboxyl end, well, let's just go on. It has this carboxyl end, and here we're going to pull off a hydrogen and an OH group, and that's going to connect these. Okay, so that leaves us with carbon, oxygen, and then this carbonyl group right here. Okay, this is called an ester linkage. Just remember, ester linkage is associated with the fats and oils. It's this link here between the glycerol and the fatty acid. This link between the oxygen and the carbonyl group, but between a glycerol and fatty acid. Ester linkage. Okay, let's look at the overall structure. So here's our glycerol group, and then we've got 1, 2, 3 fatty acids. Okay, so let's go down this next diagram. Okay, so triacylglycerol, here's kind of a simplified version of it. Glycerol plus 3 fatty acids. Glycerol and 1, 2, 3 fatty acid chains there. A little more detailed diagram. Here's our glycerol. These are our ester linkages tying the glycerol onto the fatty acid. Then this fatty acid is just this chain of carbons, and you notice this chain right here, all the carbons are connected by single bonds. That would be a saturated fatty acid. Go down here, this one, we have some double bonds in here, and this would be an unsaturated fatty acid. Now, the name saturated fatty acid means that that chain is saturated with or loaded with hydrogens. Here, notice where we have the double bond, we can't, this carbon already has 1, 2, 3, 4 bonds around itself, So it can't have the two hydrogens on there. So unsaturated. It is not loaded with hydrogens. But the key feature is that where we have this double bond, it puts a bend or a kink in the chain. And that kind of spreads these chains apart away from each other. Okay, so let's look at this. So here's our ester linkage. This is the bond between the glycerol and the fatty acid. So right there, the oxygen to the carbonyl group, and then pointed out up here, of course, R and R, that's the remainder of the molecule. And that's just kind of an organic molecule. The R group represents an organic molecule. Okay, this triacylglycerol, saturated and unsaturated fatty acids. Let's look at that. Unsaturated fatty acids. This is where carbons are bonded by single bonds, forms a straight chain. Saturated fatty acids allow the fat or oil to act as a solid. These are associated with the animal fats. Unsaturated fatty acids, we've got one or more double bonds between the carbons in the chain, and the chain is bent at each double bond. And this spreads chains apart away from each other and causes this to act as a liquid rather than a solid. And the unsaturated fatty acids tend to be associated with plant oils. Now, this idea of the saturated fatty acids being associated with solids and associated with animal fats versus unsaturated fatty acids being associated with liquids and plant oils, that's a generality rather than an absolute difference. You will have some animal fats which will have unsaturated fatty acids in them. Likewise, you will have some plant oils which will have saturated fatty acids. So these are general differences, not absolute differences. Okay, so here's our triacylglycerol with 3 saturated fatty acids. Glycerol, and then notice it's all single bonds between the carbons, and each carbon has 2 hydrogens on it that form straight chains. Okay, those straight chains can lay in close together. This acts as a solid. Here's triacylglycerol with 3 unsaturated fatty acids. And right here, each place where we have a double bond, it puts a bend or a kink in the chain, and this spreads the chains out apart from each other, causes this to act as a liquid rather than a solid. So the unsaturated fatty acids associated with the oils, saturated fatty acids associated with the solid fats. Okay, so we also have these terms monounsaturated fatty acid and polyunsaturated fatty acid. Mono means one, poly means many. A monounsaturated fatty acid has 1 double bond in the chain. Polyunsaturated fatty acids have 2 or more double bonds in the chain. Margarine and shortening, those are something that most of us are going to have in the kitchen at home. And if you look on a container of margarine or shortening, or a lot of other manufactured food products, you'll find the phrase hydrogenated vegetable oil. Okay, hydrogenated vegetable oil consists of unsaturated fatty acids, which, in other words, plant oils, that are chemically processed to break those double bonds and add a hydrogen. So what we're doing is synthetically changing this unsaturated fatty acid, this liquid oil, to a saturated fatty acid, which allows the triacylglycerol to form a solid. Okay. Now then, we have this term trans fatty acid. This has been in the news for about the past decade or so. On a lot of food packages, you'll see the phrase partially hydrogenated vegetable oil. So when they attempt to do this, in many cases, not all the double bonds are broken. Some of these double bonds are converted from a cis arrangement to a trans arrangement. Okay, so we want to look at this trans configuration and cis configuration. The trans configuration straightens a chain and forms a solid. So here's our cis configuration. Cis means next to or adjacent to, and the hydrogens are on the same side of the chain, and they push away from each other and put this bend in the chain. Here's the trans configuration, and we still have a double bond, but this time, because these hydrogens are across from each other, they're not pushing away from each other, and it allows it to straighten out the chain. And by straightening out the chain, it allows this fatty acid to be associated with a solid rather than a liquid, which that's the goal of this conversion, is to convert this to a solid. Now, the reason that we've heard so much about trans fatty acids in the news over the last decade is because trans fatty acids pose more of a health risk than do naturally occurring saturated fatty acids. So, trans fats tend to raise the low density lipoproteins and lower the high density lipoproteins. These lipoproteins are the carriers for cholesterol. And basically, a lot of times you'll hear this phrase that low density lipoproteins are the bad forms of cholesterol. These are the ones that contribute to plaque in the vessels. The high density lipoproteins, that's the good form of cholesterol. This allows cholesterol to be carried back to the liver to be processed. So, trans fats raise the bad stuff and lower the good stuff. Saturated fats will primarily just raise the bad stuff without affecting the good stuff, the high density lipoproteins. So, the trans fatty acids basically hit us with a double whammy. It raises the low density lipoproteins, lowers the high density lipoproteins. Also, these trans fats tend to stay in the bloodstream longer than saturated fats, and that allows for more opportunity for the trans fats to enter the cells lining blood vessels and form plaque. So the overall effect is that trans fats increase the risk of cardiovascular disease more than saturated fats. Now, kind of like earlier when we talked about fructose, you have fructose as a naturally occurring sugar, and then you have high fructose corn syrup, manufactured material. Same way with these trans fatty acids. Trans fatty acids are naturally occurring. In beef, about 2 to 5% of the fat in beef will contain trans fats. But in some of the older margarine and shortenings that contain partially hydrogenated vegetable oil, trans fats could, at least at one time, account for as much as 15 to 45% of the fat content. So, yes, trans fats are naturally occurring, but they occur at a lower rate than what they do in the partially hydrogenated vegetable oils. Now, over the last several years, you see a lot of food labels that tout that they are trans fat free, so apparently it's fairly easy for the food science folks to figure out how to manufacture foods without trans fats in there. Okay, so that gets us up to essential fatty acids, and an essential fatty acid is a fatty acid that is required by the human body, but the human body can't manufacture it. It has to be included in the diet. Anytime you see that essential nutrient, it follows that definition. It's required by the human body, but we cannot manufacture it, so it must be included in the diet. Okay, then we get into some other lipids, and we'll have to cover those in another video. So we'll stop here, pick up in the next video. Thank you.